Most popular number system is decimal. We use it, and digits are okay. I have a mistake in forming this lines. Better make it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Can you find any other digits other than 0 to 9? I don't think so, because every number is made of this. Similarly, as decimal system, there are other number systems. Okay, so these are four standard number systems. One is decimal. We are very much familiar with it. And base is 10. Here binary system, the number of digits used in binary systems are 0 and 1. Similarly, and its base is 2. And for octal number system, number of digits are 0 to 7, base is 8. And for hexadecimal number system, the digits are 0 to 15 actually. So since after 9, after 9, the two digits are making these digits. So as a result, we are representing using alphabet. That means after 9, we can directly tell the digits are A, B, C, D, E, F. But A means 10, B means 11, C means 12, D means 13, E means 14, and F means 15. Now, from this table, can you tell me what is base? If I ask that question, what is base?
Sir, number of
Divided.
number system.
Exactly. This is very popular question. He asked in exam or in type of viva, what is base? So from that table, it is very clear that number of digits used in number system, used in a particular number system to represent a number is known as base. Okay. A number of digits available in a number system to represent a number. Okay, so I don't need to explain the base, but one thing I can explain, if it is R-based system, let's say number of, sorry, here I should not write in this. Let's say the base is R. Okay, here. Okay, move to next page. Here, I have some problem with the page. If your number system is of R base, okay, so numbers will be 0, 1, let us check from the, if it is 10 base, then 0, 1, 2, 3, 8, 9, but not 10, before 10, okay, 0 to 9. But total numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Similarly, for binary system, since base is 2, total numbers 0, 0 and total numbers are 2, but it starts from 0 to 1. Similarly, for octal number system, total numbers are 7, total digits are 7, but it starts from 0 and runs up to 7. So that's why actually if it starts from 0, it, and that is also true for hexadecimal, since base is 16, so it runs up to 15. So for R-based number system, I think if total digits are R, so it is represented, or total digits in a number system is 0 to, no, digits in a number system is 0 to R minus 1, total digits are R. Okay, total number of digits. Actually, these terms are very confusing often. Equal to R. So, if I can generalize that system or number system, we will get that idea. So now we have to understand one by one, because number systems are quite similar. If we can understand one of them, then I think the rest of them you can very easily understand. Okay. We'll focus on binary and decimal number system because decimal is mostly used, and binary is the system, is the internal mechanism of computer system, because computer system responds only high voltage and in presence of high voltage and low voltage. So as a result, its internal system, the operation within its internal system supports binary information, or whatever we have to instruct to computer system, it has to be binary. So everything is binary inside computer system. So that's why we have to know about this number system a little bit in detail. And other number systems are also used, because hexadecimals are used for addressing in microprocessor type of thing, and octal is also used some other purpose. So these four are popular, but it doesn't mean that only these four bases are available. You can have any arbitrary type of base, 7 base, 8 base, 23 base, whatever. But you have to keep in mind, if your base is R, or total number of digits are R, then each digits are 0 to this. Let's say I consider an arbitrary base 18, R equal to 18. So its number should be 0 to, in this way, 17. Okay. Now we get to know about conversion in binary system from decimal. Decimal to binary. Let's say there is a number. Okay. Sorry. This is a number, let's say. I have to convert it into binary. Now, how can I do this? The rule is that you have to divide the number by 2. Why is it 2? Because it is of base 2. And you have to store the quotient as well as remainder here. Okay. So quotient is 7 divided by 2. What will be the quotient?
8.
8.
8.
Reminder is
And
1.
remainder is 1. Okay. Similarly, we have to do the same thing until the quotient becomes 0. Now tell me
4
4 and
0.
0. Okay, so keep on doing. And this is 2, this is 0, this is 2, this is 1, this is 0, and this is 2, this is 0, this is 1. So somebody stops here because that is also possible. Now, this direction is very, very important. We have to read the number from backward direction. Okay. Okay. So it is nothing but from bottom to top. In this direction, we have to. So it is 1, 0, 0, 0, 1. And you can also put 0 before it, no problem. But this is actually the binary equivalent of 17. But later you will know that that is unsigned, but I am not getting into that topic because unsigned signed has some difference. But roughly you know it that it is the binary equivalent of 17. Okay. Let us do another example. Let's say your number is 41. Now divide by 2. This is 20. This is 1. Sorry, I should not write forwarding minus. This is 1. Quotient no, this quotient is 1. And this is 0. You may also stop here because it is less than 2. You may not run up to the next page, but if somebody likes to take only the remainder quotient part, sorry, only the remainder part, then you may continue your division for one more step. Okay. So 41 is equivalent to 41 in base 10 is equivalent to 1 0 1 0 1 0 0 1. This is in binary. So here we write in this way also. Okay. If it is another base, let's say it is R base, we have to convert decimal to R base. Here I have taken R equal to 2, nothing but. Binary is nothing but R equal to 2. So you have to divide number by R. You have to successively divide the number by R. Okay. And you have to accumulate the remainder, and then you have to read it from bottom to top. This is the general idea of converting number from decimal to R base. Okay. Here I have used R equal to 2. Okay. For binary.
Sir, I have doubt.
Yeah, you have doubt. Please tell me what is your doubt.
Why do you write the 41 base 10, sir?
41 base 10, it means it is the representation that it is a binary decimal number. Because you can see that in octal number 41 can also be a digit. In hexadecimal number there 41 can also be a digit. So if I write only 41, so it doesn't mean that it is always a binary. Okay, sorry, decimal number. So that's why If it is decimal, then you have to write 41, then 10 as a subscript. If it is octal, you have to write in this way. If it is hexadecimal, then you have to write in this way. But these numbers are not same. These numbers are not same. But this number, if you simply write 41, although by default we understand that it is a decimal number, but when you are dealing acutely with the number system, then there may be some other numbers, numbers with different base.
Yes,
So
sir.
that's
Understand.
the extent with I have written in this way. Same thing I have also written for binary. That this thing is for binary. You can also write the same thing in decimal number. In decimal also it has some value. Okay. In decimal it is known as 11. Okay. That's why. Okay. Now we'll do the reverse. That means so far we have converted a decimal number into binary. Now we'll convert it back into decimal to check if the conversion is done properly or not. Okay. So you have to know the rules how to convert binary into decimal. So before converting binary into decimal, just forget about the number system. In your class 6 or 7, I think you had faced a kind of problem that if two digits of a number are x, y, then what is the number? Let's say two digits are x and y. Then what is the number?
10x plus y.
10 into x plus y.
10x plus y. Now, how can you say this? Because
Sir, because it is decimal system.
in decimal system, and not only that, the weightage of this position is
So we know the
10
place
to the
value.
power 10 to the power 0, and weightage of this position is 10 to the power 1, since it is a decimal number system. Okay. I am providing one more example because this concept is very, very vital for converting a binary system into decimal. If you can understand, then everything will be clear. Let's say it is 18, whatever. Then it means it has weightage of 10 to the power 1, it has weightage of 10 to the power 0. So 10 to the power 1 into 1 plus 10 to the power 0 into 8. So actually this is the number. So it is 10 plus 8, nothing but 80. We will apply the same principle here. If it is a binary number, if xy is a binary number, then its weights will be 2 to the power 0, 2 to the power 1, and not only that, if digits are like x1, write it from the backward. If digits are x1, x2, x3, x4, x5, x6 like this, then its weightages will be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. So in this way it will continue. It will be 2 to the power 6. So in this way we will continue, and what will be the number in decimal? It is nothing but 2 to the power, it is x7, say 2 to the power 6 into x7 plus 2 to the power 5 into x6. So in this way, ultimately 2 to the power 0 into x1. So this is the number in decimal system. Same principle we apply for conversion of binary into decimal. Let's say 17 is nothing but 10001. So 1, 1, 0, 0, 0, 1, is it? I think so. 1, 0, 0, 0, 1. Now, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. So 2 to the power 4 into 1 plus 2 to the power 3 into 0 plus 2 to the power 2 into 0 plus 2 to the power 1 into 0 plus 2 to the power 0 into 1. Please tell me what is the value. 2 to the power 4 into 1, it means 16. These things are 0, 0 and 0, and this is
1.
so it is nothing but 17. Is it clear to everybody?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
okay. So let us convert 41 also. So 41 means 1 0 1 0 0 1. So 1 0 1 0 0 1. Two to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and 2 to the power 5. Is it? Let me check. I have forgotten the pattern just. 1 1 0 1 0 0 1. Now 2 to the power 5 into 1 plus 2 to the power 4 into 0 plus 2 to the power 3 into 1, 2 to the power 2 into 0, 2 to the power 1 into 0 plus 2 to the power 0 into 1. Now tell me what is
32.
this? Okay. 0,
8.
8. 8 plus 0 plus 0 plus 1. So 32 plus 8 equal to 40 plus 1. 41. So I think you can convert. Now if your number is of R base, x1, x2, x3, x4, x5, if it is of R base, then its weightages are r to the power 0, r to the power 1, r to the power 2, r to the power 3, r to the power 4, r to the power 5, in this way. So ultimately, what is the number in decimal? It means r base to decimal. It will be r to the power 5 into x to the power 6, x6, not x to the power 6, r4 into x5. Actually, in this way, actually r0 into x. Here r is equal to 2. Okay. In our example, we have used r is equal to 2. So anything, if your number is decimal or other than decimal, that means if it is octal, hexadecimal, or any other base, any arbitrary base, if you know what is the base, then you can very easily convert number into decimal. Okay. So if I give you an octal number, if I give you hexadecimal number, if I give you a base 21 number, whatever, it's not a big issue. Somehow you can convert it into decimal. Okay. Now you can very easily see that if number is in decimal, you can convert it into R base for R equal to 2, it is binary. Okay. Just I'm reminding you some slides because decimal to R base. We can convert. Now for any base to we have the option to convert from any base to decimal also. Okay. So R base to decimal conversion is also possible. Now can we convert from R base to M base, let's say? Just tell me if you have any idea or not. Based on you tell me what is your solution. Tell me, no problem.
Dividing by m and taking remainder.
No, that is the procedure we are talking about. But what is the idea? That means if your number is in R base, you have to convert it into M base. That means any base to any base. If I like to convert, then is
So we have
it
to
possible?
convert it first to decimal.
Decimal, exactly. So R base to decimal, you have to convert. And then you have to decimal to M base.
Sir, there is no direct method?
If there are some direct method for some bases only, specific base, but there is no such generalized method actually that we can convert from any base to any base. For some base, let's say I will also show these examples. There is a method for converting directly. Let's say from decimal binary to octal, binary to hexadecimal, octal to hexadecimal. There are some methods are there, but mostly this is the general way of converting any base to any base. Okay.
Yes, sir.
This is very important for your exam because sometimes this type of question comes up that if it is your question. Like this, and actually this is not an example. This is an example, but the idea is this: you have to firstly convert into decimal, and then you have to convert into M. Actually, I have skipped one very important thing, that if your number is integer, then it is okay. But if your number is not an integer, if it is fraction, if your number is like 41.6875, if it is like that, then how can you do this? Okay, how can you convert into binary, and how can you convert it back into decimal?
Sir, we can break
We can
it into two parts.
divide it into two parts.
Sir, what? 41 plus 0. No, sir, break into two parts. Then 41 part is like general method, and 0.6875 part via multiply with 2.
And that is, you know the method previously, that's why you are talking about it. Okay, this is the way we do it. We first split it into two parts. One is integer, another is fraction part. Okay. 6875. Okay. Now in integer part, I think what is the value? I am not going to do it once again because it will take some time. 101001. Check it from your copy also. This is
Sir, is the number is base 10?
this number is base 10. Okay. 41.6875. It is in base 10. If nothing is specified, you can consider it is base 10 number. But if it is something else, then the base will be specified. Now 41 is 10001. I think you have already done it. Now how can we convert it into binary? Okay. Here the rule is you have to multiply by 2. Actually 2 is for binary. Here I am using 2. You have, in general, you have to multiply by r. Okay. Multiply by 2 and then tell me what is the result. What is the result? Use your calculator and tell me.
1.375.
1.375. Okay.
Yes, sir.
And now you have to extract the integer part from it. Integer part is 1. Okay. Integer. Understood? Now, other than integer, you have to divide the multiply the fraction with 2. Tell me the result.
0.750.
0.750. Okay. Integer part is 0 here. Then 750. Multiply by 2 once again and tell me the result.
1.5. 1.5.
1.5. So integer is 1. Now 0.5.
1. 1.
1.0 and it is 1. And what that is, I think after this step it is useless to carry on because everything will be 0. Okay. So you have to read it from top to bottom, not bottom to top. Okay. Because I can go back to some slides before that. We had read here while converting decimal to binary, and it is in only integer, then we have to read the information, that means remainders, series of remainders from bottom to top. But here actually we have to read it from top to bottom. Okay. So after reading, what is the value? 1011. So before that, we have to put radix point. Here you don't call it decimal because in decimal system we call it decimal point. In binary system it is binary point. But in general you call it radix point. Okay. So ultimately your number is this one. 101.1011. Okay, this is the binary of this one. Sometimes it is not always reduced to 0. You can understand what does it mean. The recurring occurs here. So you have to carry on up to 5 to 6 decimal radix point places. After radix point, you have to take 4 to 6 digits, not more than that, if nothing is specified. Okay.
Sir,
Now, yes,
sir, why we have taken r equal to 2?
because this is I am supposed to convert into binary. That's why r equal to 2. If I have to convert this information into octal number system, then I have to multiply it by 8, 8, 8, 8. You just try to understand the general idea of it. Okay. Any
Okay.
number, if you convert into that base, you have to multiply that base if your number is fraction. Otherwise, you have to, if it is integer, you have to keep on dividing and collect the integer. But that divisor, I think, is no, is that radix r. Okay. Now we had done it. I go back to some slides before. This is yes. We had discussed this weightage for integers. If it is fraction, what happens? These weightages are negative. Okay. That means, let's say x1 dot x2 dot x3, this is the number. Okay. Then weightages are, since it is before radix point, so it is 2 to the power 0, but after radix point, these numbers are 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. So in this way, actually 2 to the power minus 4, 2 to the power minus 5, 2 to the power minus 6. In this way, it will go on. So as a result, this is 1011. Its weightages are here 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and 2 to the power minus 4. But here actually 2 to the power 0, 2 to the power 1. In this way, actually the positive part of 41 will be. Any problem to understand this? Okay, let me. I feel that some of you have some difficulty in understanding it because you are learning it for the first time. Let me do it from the beginning. If your 41 is 10101001, okay, 101001 and point 1011. So let us put the weightages here. This is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. And here it is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and 2 to the power minus 4. And if I compare directly with the decimal number system, like let's say it is 4, 1, 72, 0.72, let's say. This is the decimal number system. Okay. Then this weightage is 2 to the power minus 1, 2 to the power, sorry, this is everything. I am a little bit confused. This should be, so if it is decimal, then how can we interpret the number 7 into -1 plus 2 into 10 to the power -2? Now tell me what is the result here? 0.7, I think.
0.7.
And this is 0.02.
0.02.
And now it becomes 0.72. So if you are clear with this concept, then you can very easily find out. Now I will rather not do the integer part here because you have done it. It will make the operation clumsy. So 1011. So if it is 2 to the power -1, 2 to the power -2, 2 to the power -3, 2 to the power -4, then there is point before, then 1 into 2 to the power -1 plus 0 into 2 to the power -2 plus 1 into 2 to the power -3 plus 1 into 2 to the power -4. Now tell me what is the values? What are the values?
0.5.
0.5. This one. Use your calculator.
0.25.
0.25.
0.
Sir, 0.
Okay.
0 into.
Oh, this is 0. This is 0. Okay. Yeah. Now this is
0.125.
0.125. And this is
0.065.
0.065.
625.
625.
Sir, 0.0625.
0.0625. Okay. Now sum them up and tell me. Sum these up. 0.6875.
0.6875.
6875. So I think if I go back, this is the same as this 6875. So our rule is correct. That means we are able to convert it into binary and convert it back into decimal again. Okay. So this part will be 41 and this part is 0.6875. So together this is nothing but 41.6875. Is it clear to everybody?
Yes, sir.
Okay. Now similarly, I will show that how can I convert it the same thing into octal number and hexadecimal number 6875. Let's say this is decimal. I am trying to convert it into octal. So what is the rule? You divide by 8. You just tell me. Is it?
Yes, sir.
Then it is nothing but 5-1. The integer part is 5-1 and 6875 if it is sorry, I have forgotten to put the heading. You can also know decimal to octal. Then multiply by 8. Actually, if it is problem to some people. You look at this. While I was converting this number into binary, that's why I was multiplying by 2, and now I am multiplying by 8. Now tell me the result.
5.5.
5.5. So integer is 5. Next,
4.0.
4.0. Integer is 4. So I don't need to continue anymore because 0 comes here and 0 multiplied by whatever it becomes 0 constantly. So it is from top to bottom. So ultimately the number is 51.54. So this is octal. But what is the proof that it is converted from decimal to octal? Now we'll try to convert it back into decimal. Okay. So 51.54. Now weightages are 8 to the power, this is 8 to the power 0, 8 to the power 1, this is 8 to the power minus 1, this is 8 to the power minus 2. So 5 into 8 to the power 1 plus 1 into 8 to the power 0 plus 5 into 8 to the power minus 1 plus 4 into 8 to the power minus 2. Now tell me these values. 40, I think. This is 1.
1.
This is
0.625.
0.625. Okay. Then
0.0625.
0.0625. Is it?
Yes, sir.
Okay. I am not calculating. Then sum this up and tell me.
41.6875.
So our rules, there is no such problem with the rule. Okay. We can convert it into octal and we are also managed to get it back into decimal. No problem. Okay. I think you know it. Now let us check the same value for hexadecimal. Okay. If I can convert into hexadecimal or not. 41.6875. Now our target is to make it base 6. Base 16. Now 41 divided by 16, then what is it? I think it is 9. Then 0, then 2. Is it? Check it.
Yes,
I am
sir.
not very strong at mathematics actually. Now, so I think it is 29. And if it is 6875 into then 16, then what is the result?
11.
11. 11 point what? 0.
Yes, sir. Yes, sir.
11.0. Then we don't need to carry on because our fraction part is 0 and integer part is 11. So 11 means what? Actually, we had B exactly. Then I am referring also that slide because for some people still it is a new lesson. 10 means A, 11 means B, 12 means C, then 13, then 14 means D, F. So 11 means B. So actually the number is 29 point B. Okay. In hexadecimal. Okay. Now similarly, let us check it if it is the decimal of this or not. So we put here the weightage of this digit is 16 to the power 0, 16 to the power 1, this is 16 to the power minus 1. Now, so what is it? 2 into 16 to the power 1 plus 9 into 16 to the power 0 plus B means here actually 11, so 11 into 60 to the power minus 1. Now calculate this and tell me. This is 32, I think. This is 9. This is
0.6875.
6875. So I think it is 41.6875. So now I think it is very, very clear how can I convert any number to any number. Okay. Is it? So let us take a break for 10 minutes, then I will continue. Okay. So after the break, let us continue the lesson. So far we have learned from converting anyways to anyways to decimal system, but there are some shortcuts rule you have to remember. If the derivative steps of this conversion is not required in your examination or that, then you may use this type of things. But if you are asked to convert, you should not use it, because these are for your shortcut or getting quick results. Okay. So shortcuts for decimal to binary. Let's say we have to organize the weightage first. That means 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Okay. So what are these in form of decimal? This is 1, this is nothing but 2, this is 4, this is 8, and this is 16. Similarly, 32 is also possible. 2 to the power 5, 2 to the power 6 is 64. So these are the weightages of a binary system. I have considered only the positive part. Now, if you are asked to convert it any number, let's say it is 17, 41, like that. If it is, you have to choose, mind it. You have to choose the first number or the highest number number among these, which is just below or equal to, which is less than equal to this number. Okay. I repeat once again because it is confusing to some people. You have to choose among these numbers. Okay. Among these numbers, you have to choose a number which is less than equal to this number. Okay. But this number should be highest. Okay. So let us write highest number less than equal to n. If you are trying to convert n into binary. Okay. So now in that case, what is the highest number less than equal to n? Tell me. 16. So
16.
we put 1 below 16. Okay. Actually, I am discussing that thing very slowly, but when you are get used to, you can find it instant. Okay, no problem with it. Okay. Now you have selected 16. So let us reduce the number by subtracting that highest number. So the number becomes 1. Okay. Now tell me, what is the highest number less than equal to 1?
1.
1.
Now we don't need to carry on, because if I subtract 1 from here, it becomes 0. So here we will stop the process. Now we will put 0 for rest of the numbers. So check it if it is equivalent to 17 or not.
Yes, sir.
Okay. Then let us do it for 41. Find the highest number less than equal to 41.
32.
32.
So when I subtract 32, sorry, so it becomes 9.
9.
So highest number less than equal to 9, 8. Okay. Subtract 8, then highest number less than equal to 1.
1.
1. Then we'll put 0 because after that it will be 0. Let us check if it is equivalent to 41 or not. But I think it is 41. But do not apply this rule for rest of the number system, but it may not work properly. I think it will work, but if you are asked asked to convert a number from decimal to binary, then you do not use this because this is just for getting quick results. Similarly, if your number is this in binary, then how can you get the decimal form of it? You will just sum up the numbers containing 1 below it. Okay. So here actually we'll add 16 plus 1. Here actually we'll add 32 plus 8 plus 1. Check it. If it is 17 or if it is 42 or 41 or not. Is it okay?
Yes, sir.
Okay. There is some problem with the screen. Now, binary to octal directly without using decimal as an intermediate form of it. Okay. Binary to octal directly. So let us get one binary number. This is 41.68. What is the 101001? This is 41. 101001 point. What is 68.75? I think it is 1011. Is there any blank slide? 1011. So this is, I am supposed to convert directly into octal. Okay. Since it is octal, octal means base 8. 8 means 2 to the power 3. So I am highlighting that number. Okay. 3. Highlight this number 3. Why I am highlighting? Because I will make a group of 3. This group, if the number is on the left of radix point, this group will start from here in this way. And on the right, it should be like this. This is not a group of 3, but you can add 2 additional zeros. And here, if it is not group of 3, you can add additional zeros on the left. After radix point, if you add 2 zeros, so it does not change your value actually. Now, tell me, what is the binary of this? What is the binary of this? What is the binary of this? And what is the binary of this? Tell me. 2, 4, 8, 1, let's say. So 1, 0, 1. Actually, it is nothing but 5. Similarly, tell me, what is it? 0, 0, 1. Any problem?
1. Sir, 1.
1. Then
1.
this is
5.
5. This is
4.
4.
4. So it's nothing but a 51.54. So let us check the value. We had already converted this. It is 51.54. Okay. Let us do the same thing for hexadecimal. It is also possible. So number is, I think, 101001 101001 1011 1011 1011. Now hexadecimal means 16, base 16. Base 16 means 2 to the power 4.
4.
So I am highlighting this number. So we'll make a group of 4 here instead of group of 2, 3. Okay. What is the decimal value of it? Tell me. What is the decimal value of this? 001
2.
0. 2.
Yes.
Then
9.
this one 9. Then
B.
P means 11.
Yes, sir.
11 on P. Okay. So it is 29 point B, I think, in hexadecimal. So let us check. It is 29 point B. I think right now anything is possible. You can convert any number into any base, convert any base number of any base into number of any base. You can convert if it is binary number, then you can directly convert into octal and decimal, octal and hexadecimal. So there is no such problem. I think you have learned to deal with these number systems. Now I will get into the detail of binary, because binary has different types of representation, especially in computer system. Right now at your stage there is no that much of detail in arithmetic. binary arithmetic, but little bit you have to know, and especially if the number is fraction or number is negative, then what happens? Fraction I think we have already know how to deal with, but if number is negative, then what should we do? Or like that. We have to know the different types of representations in binary. Okay. So this is the total representation of binary numbers. So far we have learned unsigned binary. Why is it unsigned? Because the numbers are 0 and positive only. But for signed number systems, the numbers are 0, positive and negative. We can also represent negative numbers in binary. So there are three types of signed representation. One is sine magnitude, another is ones complement, another is twos complement. Okay. So I will not discuss about the unsigned because already I have discussed so far. I have discussed how to convert decimal into unsigned binary number or like that. But this signed magnitude and ones complement, twos complement, this signed number system we have to know. Okay. Let us know these things one by one. In sine magnitude, the number is divided into two parts. Okay. One is sine value, another is absolute value. Okay. So value and sign, these two are two different things. You know that there is a distinction between positive and negative. So sign value, there is an importance of sign value here. So in sign value, we use one bit. If it is 0, then we represent it is positive. If it is 1, we represent it as negative number. And value is nothing but the unsigned representation of a number. Okay. Now what is it? consider the same example 17. I think you know what is the unsigned representation of it. 1 0 0, is it? I just have forgotten. 1 2.
Yes, sir.
Okay, it is. That means it is 16 plus 1. Now, since it is positive number, it is plus 17, so we'll add 0 before it to make it sine magnitude. And what happens if it is minus 17? Then we'll add 1 instead of 0 and value remains same. 1 0 0 0 1. So sine magnitude is a very simple form of representation. Okay. Just if you can convert a number into binary, that's enough. You will put that stream of ones and zeros as its value and place 0 or 1 before it. Okay. If it is 0 or greater than 0, then we consider it is positive number. Otherwise, it is negative. For negative number, we will put 1, and for
Sir,
positive
is it not create?
it.
Hello, sir. Sir, is it not
Hello.
create confusion during mathematical operations?
Exactly. There are some sort of confusions. Why is it so? Because in mathematically 0 is represented. If I represent 0, let's say 1 2 3 4 5. So if I represent 0 in form of 5 bits, so 0 is nothing but 0. This is also 0. But if it is a sine magnitude representation, you have to place a positive sign before it, or you have to place negative sign before it. So same, although these two numbers are same, you have to use two different patterns. There is mathematically plus 0 and minus 0 doesn't exist. These two things are same. But here actually we have to represent it in differently. Okay. So that is actually the root of confusion. Two zeros. This is the problem. And let us check what is happening for one's complement. For one's complement, you have to build a positive number. Whatever be the number is, you have to make the positive number first. Okay. Positive number first. As mentioned in, or better to say like, sine magnitude. That means, like sine magnitude representation, we have to build the positive number first. In sine magnitude representation, what is the format of creating positive number? You place the value and place 0 before it. That is nothing but the positive number. Okay. So in this step is also used for creating one's complement number. Okay. And then interchange 0 by 1 and 1 by 0. Okay. Let us consider 17 only, because if I use too many example of too many numbers, it will be confused. So let us convert the same number in different formats. Okay. So it is 1 0 0 0 1 for, and if I place 0 before it, then it is nothing but the sine magnitude representation. But the first thing what you have to do in one's complement, you have to create a positive sine magnitude representation of it. Okay. Then if it is positive number, then do nothing. If the number is negative. Okay. And do nothing if number is positive. So if it is plus 17, then we don't do anything. Okay. We'll write that 0 1 0 0 0 1. This is the representation, one's complement representation of plus. But what happens to minus 17? Actually, you have to convert this pattern in this way: 0 by 1 and 1 by 0. So it is nothing but 0 1 1 1 0 and 1. If you check the sign, it is automatically getting negative. So this is nothing but the representation of minus 17. Okay. Any doubt in this procedure?
Sir, once again.
Once again, okay. So you have to, whatever be the number, you have to make the positive sine magnitude representation of it. Okay. That means you will place the value, and on the left of the value, you will place the sign bit. Sign bit means, here I haven't discussed what bit is. I should have, the binary digits are known as bit. Okay. Binary digits are known as bit. Okay. And 8 bit equal to 1 byte. You know it, because sometimes I use this term, bit and byte. So binary digits are nothing but bit. Now bit. Now if you can check that this is sign bit of sine magnitude representation. Sign bit is 0 if number is positive, sign bit is 1 if number is positive. So when we are preparing plus 17, so we had written the value of it and then place 0 before it, because it is plus 17, and here we just switched the only the sign bit. We didn't do anything on the pattern, on the value. But here actually the rule is like that. Here the rule is you have to make the positive number first as per the rule of sine magnitude representation, but instead of switching only the sign bit, you have to switch the entire pattern. Okay. So entire pattern by 0 by 1 and 1 by 0. Okay. So this is the negative representation of 17. Understood?
Yes, sir.
Okay.
Sir, how to check it's minus 17?
How to check it? Always you check the sign bit. If your sign bit is If your sign bit is 1, then you can tell it that it is a negative number. And you can also check it also. You convert it back. If you like to convert it back into positive, then you interchange 0 by 1 and 1 by 0. Then what happens? You will get the original number back. The rule is that if your number is positive, you can make it negative by 1's complement conversion, and same thing is also true for negative to positive. Okay, let's say it is 17 here. If you do 1's complement on it, it becomes minus 17, and if you do 1's complement operation on 17 minus 17, it becomes 17. Okay, this is the rule for converting 1's complement. Any doubt?
Sir, can two decimal values have the same binary values?
Can two decimal values have the same binary value? Same thing is true for here actually. If your number is 0, other than 0 I don't know, but if your number is 0, its positive representation is this 0, but its negative representation is also this. That means this is nothing but the minus 0 and plus 0. So from the perspective of binary representation, minus 0 and plus 0 is same, but here you will get two different patterns. So that is the problem here also persists, that two zeros, problem of two zeros. And what is the problem? Since you are making combination with some bits, so here one of the pattern is already occupied as it is, and it is creating such type of redundancy that two patterns are representing same type. Okay, so that's why you are stopping from, you are actually restricting the range of the numbers represented by 1's complement.
Sir, like 101110 is also equivalent to 48. That's why.
10.
That, sir, what minus 17, sir.
Minus 17.
Sir, 101110.
101110, is it?
Yes, sir. Sir, if we are converting it, yes, sir.
If we are converting it into
Decimal, sir.
Then
it's equivalent to 48, I think.
No, that is the problem. What we usually do, actually, you are converting the entire thing into decimal, but that is possible when you are dealing with unsigned number. But for signed number, you have to separately convert. You have to do something for your sign bit and do something for the value. Here, the total string cannot be converted. Okay, so you have to convert this part only if you like to get it, and it should not be converted in this way. You have to get the positive from negative number. You cannot extract the value directly. You have to convert each positive version, and then you have to remove the sign bit and convert this part into decimal. Okay. That is the difference between the unsigned conversion and sign bit conversion. If you like to get the value of a negative number, then you have to convert it into positive number. You have to remove the sign bit and convert the value into like an unsigned value and then you place negative sign before it. I will
Okay.
this type of example I will also discuss, because if I keep on discussing these things, maybe it will be very difficult for you to understand. So I will also discuss that example when I discuss the subtraction using 2's complement addition. Okay. Now 2's complement. In 2's complement, actually, the rule is almost like 1's complement. So I'm copying some part of that rule, but I will make little bit of modification. Okay. So I'm copying this part. But I have to modify also. This is not the absolute type of make the positive number first, like unsigned representation. There it's a true, but here actually, if the number is positive, do nothing. That is also true. If number is positive, do nothing. Write it first. If number is negative, then from left, from right. Actually, I am writing because this is very informal term. You have to write from LSB. Okay, LSB. I right now you will not understand. Some of you at least. So that's why I am writing from right up to left, from right to left. Keep the pattern unchanged up to first one. Then 0 by 1 and 1 by 0. Okay, this is the rule actually. So let me explain the rule first with an example. Let's say it is 17. So you have to make the number first, make the positive number first. If it is 17, you make it 17. So 1 0 0 0 1, and before that is 0. If it is positive number, do nothing. So 2's complement representation of 17 is this. So clearly the positive number representation is same for sine magnitude, 1's complement and 2's complement. But what happens to negative number? If you are supposed to get minus 17, then 0, 1, 0, 0, 0, 1, this is up to first one from right to left. That means this one. At the beginning you are getting 1. Okay. So up to first one from right to left is this one. So this one should be unchanged. Okay. Then 0 by 1, 1 by 0. Then that means 1, 1, 1, 1, 0 and 1. This is the 2's complement representation, or minus 17. It is equivalent to minus 17 in 2's complement. Now the same thing is true for plus 17, because if your number is n and if it is positive, you do 1's complement operation to make it negative, and you do the again 1's complement operation to make it positive. Same thing is true for 2's complement also. If your number is n, so you do 2's complement operation to make it minus n, and if you do the same operation on minus n, it will be positive number. So let us check it. If you can get the 2's complement, so what is the 2's complement? Up to first one unchanged, so up to this is unchanged, and then 0 by 1, 1 by 0, 0 by 1, 1 by 0, so it becomes this number. Okay. Let us do another example. Let's say 38. Number is 38. What is the binary? 1, 2, 4, 8, 16, 32. So this one and this one. Is it? Check it. Is it the binary of 38?
Yes, sir.
If it, okay. It is 38. So 1, 0, 0, 1, 1, 0. So if I have to get minus 38, then how do we get it? You place sign before it. This is the positive 38, and in 2's complement you do 2's complement operation of it. That means up to first one, this one should be unchanged, and here you will make your change. Okay. So 1, 0, then 0, 1, 1, 0, and 1. Okay. This is minus 38. And if you do the same thing on it, then up to first one, 0 and 1, then it is unchanged. So up to this will be unchanged. So 1, 0, and then 0 by 1 and 1 by 0. So this is 1, 0, 0, 1 and 0. So I think it's clear to you that from 38 to minus 38. Okay. Here let us check if there is any problem of 2, 0, 2. So let's check 0. What is the representation? 5. Let's say 5-bit representation of a 0. So the sign bit is 0. It is the positive number, and now convert it into 2's complement. So there is no first one, okay, first one. So up to this, it will be unchanged. So 0, 0, 0, 0, 0, 0, okay. Similarly, if you do 2's complement over it, then it becomes the same number. So there is no such problem of 2 zeros, only 1 0. Okay, so that is the advantage of 2's complement over 1's complement. Okay. Understood or not?
Sir, please repeat once.
This one or this one? Which one?
Sir, 60.
60. Okay, okay, okay. This is actually what is the positive 0 here in 2's complement representation? In 5 bit, let us I represent 0 by 5 bit. You can also represent 0 by 3 bit, 2 bit also. That is not. But 5 zeros, 2 zeros, these are same actually from positive side. So this is nothing but the 0 or in 2's complement representation. Now, as per the rule of 2's complement, what is minus 0? So if you do this, then we have to make the Sine magnitude representation. If number is positive, to nothing. If number is negative, then write to this one. Now you do some 2's complement operation on it. That is up to first one, from right to left, you have to keep it unchanged, and otherwise you make it 0 to 1 and 1 by 2. Okay. So where is first one here? So from right to left, if you go through, there is no such first one. Okay. So that's why the minus 0 and plus 0 is same here. Okay. Actually, you have to work out little bit. Otherwise, you cannot understand so many things after this class. Is it clear?
Yes, sir.
Yes, sir.
Not clear, then try to find what is the representation of 0 in 2's complement and 1's complement and magnitude. Okay. Sine magnitude representation. If you can do it by yourself, then everything will be clear. Okay. So if one of the pattern is not blocked by a same number, then that number can be used to represent another number. So based on that concept, your 2's complement is much more advantageous compared to 1's complement and sine magnitude. So it is very popular question in your exam, that what is the advantage of 2's complement over 1's complement. So you have to explain the concept of 2 zeros here. Now how much time is left? I think it is 10:52. Okay. No. Okay. So for the time being, I think it is okay. So you may leave. Next day I will also discuss. I think 1's complement, 2's complement, these things is okay, but I haven't discussed the range yet. Okay, next day I will continue. Right now it's not possible.
Thank you, sir.
Thank you,
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.